as the title indicates, I'm going to tell you about the large-scale computing strategy at Livermore National Lab. As the CTO for Livermore Computing, really setting that strategy and making it work is my job. First of all, strategy is really about figuring where you want to be in the long term and making a plan to get there. In some ways, so Livermore has a long history in large scale computing. I think we can rightly claim to be one of the world leading supercomputing centers. So in some ways, where we want to get to is continuing that history. And so in some ways, it may sound like it's simple. We don't want to go anywhere, but as I'm sure you all know, maintaining the position of being a world-class supercomputing center means that we have to actually move quite a bit from where we are today. And the next thing is in order to get to where you want to be, you really have to kind of have a pretty good assessment of where you're starting from. Otherwise, you're not likely to take the right road. So as I indicate here, we already have several of the systems on the top 500. In fact, 4 of the systems in the top 100. So I'll tell you a little bit about some of those, including the Sierra system, which is currently the number 3 system on the top 500. And in addition, we have a couple more systems that have only recently fallen off of the top 100, including Jade and Quartz, which are still in the top 200. In addition, we retired 2 systems that would still be in the top 100 in 2020. Those are the Sequoia and Vulcan systems. Nonetheless, lest you get the impression that we're all about running LinPack, in fact, what you'll notice is that having this many systems in the top 100 is unusual compared to other centers. And that's because we have a fairly diverse set of workloads that we end up needing to run. And so we have a large number of systems and really build different systems to address different aspects of our workload. As we plan where we're going in the longer term, one of the systems that I will tell you about today is the El Capitan system, which we expect to be one of the first U.S. exascale systems. I'm going to actually hold off talking in any detail about El Capitan until towards the end of this talk. And I'm planning to tell you some stuff that I believe this will be the first time has been covered in any open talk. So previously, this information would have been considered covered by non-disclosure agreements, but I worked with HPE to arrange to be able to cover it here. So another key aspect of where we are and where we're planning to go is that we actually have a pretty big role in the software ecosystem for large-scale systems. I'm going to touch on that a little bit, but I'm actually going to focus mostly on kind of the hardware directions. And within that, I'll touch on some of the ways that the software that we're developing enables those directions. All right. So anyhow, one of the things I'm going to focus on in this talk is that we expect what I call system-level heterogeneity to be an essential aspect of our strategy. And I'll tell you a lot more about that later in the talk. But the basic idea is that, well, today we often build systems that have what I would call node-level heterogeneity. Typically, those systems have, for the compute nodes, all just one type of compute node. So while there may be different devices on a specific compute node, the compute nodes themselves are actually homogeneous as we consider what they look like in the overall system. So Livermore is a National Nuclear Security Administration laboratory. And so that means that our center, a large portion of our budget is part of the advanced simulation and computing program of the NNSA. And so the ASC platform timeline is really a significant driver to our strategy. And when we look at the platform timeline, it's actually divided into three different types of systems. I'm going to only focus on the top two. First of all, because those are what are cited at Livermore, but actually because I think that they're the most important aspects of the overall ASC platform strategy. So on the top, we see the advanced technology systems. And these are the largest systems that ASC deploys. Right now, Sierra is the first ATS system at Livermore, and that's because we created this name, ASC created this name for the systems just a few years ago. And so previous systems such as Sequoia, which really are part of this line of systems, were not covered by that terminology. In addition, El Capitan will be the fourth ATS system, and in fact will be the next one at Livermore. Then if you look further, you'll see that ATS 6 will be the next ATS at Livermore. And we've already started thinking about how we will, what that system will look like, even though we have not actually already cited the preceding one. And so when you think about a strategy, it's actually important to have a way to have it be kind of a longer term continuum, which we see in the ATS. In addition, I'll tell you some about our commodity technology systems, or CTS, and those are also pretty significant systems, as the name would make you assume. They're driven by commodity technology. So we tend to build systems that are a little less risky than the ATS, but nonetheless can be pretty significant systems in their own right. And so I'll get to those shortly, but first I want to tell you a little bit more about Sierra, which is the most recent ATS system. I always find that difficult. I hate the fact that the acronym includes the word system, because then you want to kind of repeat systems. But nonetheless, Sierra is a 125 petaflop system sited at Livermore. Here you see a picture of it in building 453, as well as a picture of one of the compute blades. I think you've probably already heard a fair amount about what the architecture is, so I'm not going to focus on this too long. As I said, I really want to look at where we're going rather than where we are. And I really want to kind of just put out where we are to help understand how we plan to get to where we're going. So it's as you probably know, the compute nodes it's an IBM system with the compute nodes each having 2 Power 9 CPUs and 4 NVIDIA Volta GPUs. Those are connected by a Mellanox IB interconnect. The total system has 4,320 nodes. It then ends up being, those are spread over 240 compute racks. It uses about 12 megawatts of power at its peak. It also has a pretty significant spectrum scale file system. You probably think of this as GPFS, but during the course of building Sierra, IBM decided to rebrand GPFS as the spectrum scale file system. I don't know why they didn't explain that to me. I could spend a lot longer on this talk focusing on Sierra. In a longer talk, I would explain why we made some of the architectural decisions that we did in Sierra. And some of those decisions actually result in it having a lower peak per dollar and a lower impact number per dollar. But if I were giving you that longer talk, I would show you that, in fact, those architectural decisions actually do a better job of serving the workload that we intend, that we actually are currently running on the system. I'm not going to go into that in detail here. If you want to ask me questions about it later in the talk, I'm happy to try and answer them, but that's not what I want to focus on. But what I do want to focus on just briefly is that Sierra is not the only system of this architecture that we've cited at Livermore. We also have the Lassen system, and this helps kind of show some of the complexity in the way we have to run our center. Sierra is primarily intended to serve a classified computing workload, but we have a much broader workload than just that workload. And in fact, a large portion of it is unclassified open science. And the Lassen system is the system that we bought at the same time as Sierra to help, to basically serve that portion of our workload. And it is, as I mentioned, in and of itself, a pretty significant system. It is smaller. It is the number 17 system currently on the top 500. It's got 792 nodes as opposed to 4,320. And its total power consumption is more like 2 megawatts rather than 12 megawatts. But otherwise, the architecture is identical. And I'll come back to why I mention this so much when I get deeper into the strategy that we're pursuing and how we're actually advancing that strategy by things we're doing with the Lassen system. Next, I wanted to tell you about our commodity technology systems. CTS-1 is the current generation of those commodity technology systems. So the CTS target cost-effective commodity clusters. So we use the TriLab operating system software, TOS, on that. So we actually put our own operating system out there. And I'll tell you a little bit more about that in a second. We use a common environment. This is actually a set of systems that is not procured solely for Livermore. We actually, through one contract, deploy systems at Los Alamos and Sandia, as well as Livermore. They are involved to some extent in putting together TOS, although Livermore is actually the lead lab on TOS, and the contract for the CTS are run out of Livermore. The basic architecture is we define a scalable unit, and then we repeat that one or more times to build a specific cluster. Most of the systems historically have been CPU clusters, but we typically get options in the contract to be able to deploy systems with GPUs and even other alternative hardware. The contracts typically run several years, 3 or 4 years is pretty typical. And throughout that period, we buy several systems. Typically, we buy most of the systems under CTS contracts right at the beginning, but we do actually exercise options throughout the contract. All right, and these are systems that go on both our classified and unclassified networks. So Jade and Quartz, which I mentioned earlier, are 2 CTS-1 systems. The Ruby and Magma systems that are currently the largest CTS systems at any of the labs are actually what we would call CTS-1 plus systems, because they don't use the original node architecture. So we really do deploy a wide range of systems from this contract. everything from single SU systems all the way up to these very large systems that I've mentioned. So TOS is built on top of Red Hat. It's primarily, almost exclusively, built with open source software. It includes Lustre file systems, and it also includes resource managers such as Slurm. Under CTS2, we're looking to move towards the Flux resource manager, which was developed again by Livermore. And this is really our next generation resource manager. And it focuses, the reason we developed it is well indicated by, well, when we looked at Slurm, we felt that it wouldn't be able to really handle things we saw coming up in the future. And one of these things is pretty well typified by the idea of system level heterogeneity. Flux is designed so it can handle a wide range of different node types, different resource types, which is not easily done within Slurm. And I'll come back to that. In addition to the TOS, we also deploy a full development environment that's called TCE, the Trilab Compute Environment. This includes the compilers, the MPI libraries, and the tools that we run on these systems. Again, it's mostly open source software, but it's not strictly open source software, as you see with the Total View Debugger or with the Intel or PGI compilers. So I will tell you a bit about one of our more recent CTS1 systems, and this is the Corona system. So this is distinct. It's also kind of it's not the base architecture that we deployed under CTS1, which was actually an Intel CPU-based architecture. It uses AMD CPUs and GPUs. The system had originally 164 nodes. The half of those in the original incarnation had 4 MI50 GPUs. Subsequently, in the last year, we added MI60 GPUs to the other 82 nodes. We also, under CARES funding, added 121 additional nodes, which have 8 MI50 GPUs per node. So this is a pretty significant system. It's a 10 petaflop system in terms of its peak capability. It's not on the top 500. Partly that's because that's not what we bought it for. And also, to be honest, partly it's because running a efficient LINPACK over this wide range of GPU types and counts is non-trivial. But again, we didn't buy it to run LINPACK. In fact, the 121 additional nodes were added under something I mentioned called CARES funding, which was a program that the U.S. government ran in 2020 to increase the capability available to the U.S. COVID consortium. So those nodes have been largely used as part of the effort to fight the pandemic. All right, so CTS2 is the next round of commodity technology systems. We're actually in the middle of that procurement. The RFP was officially released back in July of last year. We've been, as I'm sure those of you who are involved in procurements at RECON are aware, buying large systems is not a short-term activity. It takes several years to really plan out what you want to do. And then typically we release a draft RFI for the CTS for CTS. For the ATS, we follow a similar strategy where we release draft technical specs before we release the final RFP. And then after releasing the final RFP, we evaluate the responses that we receive and then get into contract negotiations. So we're actually nearing the end of those contract negotiations. So I have a pretty good idea of what we'll be getting under CTS2. But until that contract is finalized, we won't announce what we've chosen. We expect the contract negotiations to finish pretty soon, actually sometime next month. After the negotiations finish, we'll have to submit the contract through a DOE approval process and would expect to have the contract awarded probably around May of this year, at which time we'll be able to announce what we're actually getting. It's important to realize that throughout the deployment of these systems, we're working closely with the team that's involved in siting those systems and our software team, and in particular the TOS team, to make sure that the software serves the range of hardware that we'll end up deploying under this contract. All right, so now I really want to get to the details of the strategy that we're pursuing. And in particular, this is something that we're looking at doing in some of the later CTS1 systems. We'll certainly look at doing some things under CTS2. And I'll show you towards the end of this talk how we're pursuing this strategy as part of El Capitan. I actually anticipate that the ATS-6 RFP will call for some aspects of system-level heterogeneity. Whether or not it shows up in ATS-6 is something to be determined based on the responses we see. But I would strongly expect that some aspects of system-level heterogeneity will. So when I say system-level heterogeneity, what do I mean specifically? As I said, heterogeneity at the node level is pretty common. Sierra and Lassen and Corona are commonly referred to as heterogeneous systems because we have CPUs and GPUs on each of the compute nodes, right? So those are heterogeneous nodes. However, as I indicated, we actually repeat that same node or similar node many times in the system and don't actually have a wide range of different kinds of resources deployed across the system, all right? However, if you think about some of the wide range of hardware that's being developed today, it's not clear that it would make sense to deploy that hardware in every node. So, for example, if we look at AI accelerators, it's likely that if we had accelerators really specifically targeting AI in every node, that many jobs would not make use of them. So we would have spent money on those accelerators in order for them to sit idle for large portions of the system's use. All right. So if instead we have a portion of the system that is where we locate devices of that type and make it so that they can be used within jobs that run not only with using resources in that, I don't really want to say partition because it's being used in jobs that span different types of, different partitions in a way, but it would mix different node types within the same job. All right. So that way we can then make cost-effective use of those resources. We can make sure that they stay well utilized over the overall job mix on the system. All right. As we think about future workloads, this actually makes sense, at least to me. Some of those things are one of the things that we're thinking a lot about at Livermore is something we call cognitive simulation, which is taking traditional simulation-based workloads and using AI techniques to speed up portions of those simulations. All right. So the idea of system-level heterogeneity is to use diverse node types or even different resource types by design. So this means that we move away from this kind of cookie cutter approach of we figure out one type of compute node and then we use it many, many times over within that same single system. One of the things that this gives us that's a significant benefit is we can now have a non-integer ratio of diverse node types across the system within a single job. While this may sound kind of like a radical strategy, one of the points I like to make is that it's actually pretty common in today's systems. We actually deploy a wide range of different node types, often within a single system. So a common type of node are front-end nodes, where which users log into. And then we have management nodes. We also have a wide range of node types in parallel file systems. So anyway, nonetheless, when we think about using different types of nodes and different resources within the same job, that does raise some fairly significant challenges. So one of the things that we have to think about is how are we going to partition the work, and how are we going to handle the interactions across diverse node types? So another question is, what's the right mix to use of these different resource types? How can we ensure that the architecture actually and the interconnect supports these different resource types? So we end up needing to consider questions like, what is the latency and bandwidth between these different types of nodes? And probably the biggest question is just how do the applications need to evolve to work to use system level heterogeneity? So we actually have some instances of applications that are already kind of moving in this direction, where you divide the work up kind of in a different fashion so that you can easily run different portions of the application on different resources. So in 2019, the MUMI application was won the Best Paper Award at SC19, and that was a job where we had allows itself to be built with quite a bit of asynchrony between the different portions of the job. So if you think about this, it's not really all that hard to see how you might need to be able to split up your application and basically no longer have it as tightly synchronized as normal. Most of our physics simulations actually tend to run, we run multi-physics simulations, but they tend to run one physics and then the next across all the nodes in the job. And so they have some assumptions built into them as how data flows between them, and making it so that they're not so tightly synchronous is kind of a key aspect. Anyhow, so next I was going to tell you about, we're actually already starting down this road at Livermore. We have, and specifically, we've entered into partnerships with Cerebras and Sambanova to integrate advanced AI accelerators into the Corona and Lassen systems. So we've integrated a CS1 from Cerebras into Lassen and a Sambanova SN108R into Corona. And so this allows us to explore this idea of can we use these different resources as part of our traditional multi-physics simulation workload. These partnerships include what we call centers of excellence, where we're actually working closely with both of the companies to see how we can move AI aspects of our workload to their systems and integrate it into our multi-physics simulations. We've actually already been able to run some of these models. I'm not going to detail that here on their systems. And what we see is roughly on both systems a 5x performance improvement per transistor over the GPUs that we have available on those systems. All right. And you can think of per transistor as a pretty good approximation of rough cost equivalence. All right. The Cerebrus system is pretty unique. It has what is the world's what I think of as the world's largest computer chip. It has 1.2 trillion transistors. It's a 20 kilowatt chip, so it's a pretty hot chip in its own right. As I mentioned, we've integrated that into Lassen. So what we did is we took a CS1 and connected it through the InfiniBand fabric into the standard compute nodes, and so we're now able to use it in jobs that feature that. For the Samba Nova system, you see here a picture of it being next to the rest of the Corona system, into which we've now integrated that. Both of these systems are really kind of data flow oriented architectures that well suit AI workloads. That's how they give the improvement in model performance. I'm not going to go into more than that, partly because of the technical difficulties, but also because I really wanted to tell you about some of the things that we're planning for El Capitan, the next ATS at Livermore. So this portion is largely things that have already been announced. El Capitan is a partnership with HPE. When we first contracted it, it was, of course, before HPE acquired Cray, so it was originally going to be a Cray system. We've announced that the system will be over 2 exaflops in double precision. As was required by the RFP, the peak power will be under 40 megawatts. Our estimate is that it'll be roughly 30 megawatts total. I'm not going to go into more details about that. When we first announced the system, we did not announce who the processor vendor would be because we chose to do something called late binding for the processor solution. As we subsequently announced, we're going to actually have AMD CPUs and GPUs in the system. It will have, it will feature the Slingshot interconnect. The overall partnership involves not only Livermore, but also Oak Ridge. Oak Ridge will be citing its Frontier system later this year. We'll be citing El Capitan in roughly late 2022 and early 2023, with the acceptance happening in 2023. These ATS procurements actually are very long time procurements, and they enable us to enter into a very tight partnership with the system provider. And part of that, we fund separate non-recurring engineering contracts that allow us to improve what we'll get in the overall system, but they also end up having an impact on what a company like HPE ends up offering in the systems that it sells more widely. One of the things that we're planning to do with El Capitan is actually use what I call a combination of TOS and the best of Shasta. So El Capitan will be running Red Hat on all of its nodes, and it will integrate, it'll combine that with aspects of what we do in TOS with the Shasta system software that HPE is developing. One of the NRE activities that we're funding involves something that HPE calls near node local storage. And I'm going to tell you more about that now. And HPE actually calls that the Rabbit program. So it's the near node local storage solution that they have. And this is the information that hasn't been previously discussed in a public forum. So Rabbit involves a 4U solution for node local storage, but it's more than just node local storage, which is why they call it near node local storage. What happens is you basically have PCI connections from each of the compute nodes into what they call the Rabbit S boards. All right. And that basically gives you a PCIe network that connects you to a fairly large number of SSDs and also to a Rabbit T board, which has a separate AMD processor located on it that allows you to interact with the storage independent of the compute blades. All right. Here you see an artist rendering of what we expect these Rabbit modules to look like. It's a pretty large box that will plug into the Cray, into the HPE racks, where you could also house switch modules. All right. So if you're familiar with the HPE rack design, it gives you the ability to have compute blades on one side of the rack and access them from the front of the rack, and from the back of the rack, you can put in switch blades. Instead of populating all the switch blades, which would have given us far more interconnect bandwidth than we feel our workloads need, we're actually going to populate some of those slots with these Rabbit blades, with these Rabbit modules. Okay. The software to make Rabbits work is a pretty significant aspect of how the system works. So one of the keys is, since you can actually access those SSDs directly from the compute blades, you can treat it as just a block storage device allocated to a specific compute blade. Alternatively, we can implement what we call a transient luster file system across these compute blades. So you can access it both as direct attached storage and as network attached storage. All right. So the software then provides ways to move files from these block devices or these transient luster file systems to the capability tier of the overall I/O subsystem of El Capitan. All right. So it'll automate movement between these different tiers, but they are effectively very different in how we intend to use them. An important aspect of the system software for this, for the Rabbits, is that you can access customer code in containers. So we can actually run our own code on those Rabbit processors. All right. One of the things that this reveals is that the resource manager on El Capitan will be Flux. And that's because Slurm does not really support getting allocations of these SSDs that are aware of the local compute node relationship to those SSDs. So I'm going to kind of quickly try and get through the rest of this. When we look at, and so a key here is to think about what the I/O is that we run on our large system. So there's productive output, which is really the reason we run the simulations. There's checkpoints, and those checkpoints can be one per MPI process, or at least one per all of the processes running on a given compute node. Or they can be shared across multiple processes and frequently across all of the processes in a given job. And so that's this end-to-end versus end-to-end checkpointing. All right. What we actually see in our jobs is kind of frequently a combination of these, where they maybe have a shared file that's used, that's accessed by all of the processes in the job, and then they write the bulk of their data to a single to a file per compute process. And then you can have things that are semi-defensive or semi-productive. In fact, it turns out that usually our application scientists want to use the checkpoints for subsequent data analysis. if we look at the way the compute capability is outpacing the ability to deploy large file systems, the costs would make it so that basically we can't save all of those checkpoints. For input, we tend to do much less input than output. The input can be executables, things like the applications themselves, but also operating system files and other system software files. And we have the simulation input, which may just be something as simple as the parameters of the job, or even restart data, i.e. the checkpoints that were previously output. Another important aspect of the systems is that we tend to want to use that space as a way to have extended memory, so something that we would think of along the lines of swap space in traditional systems. This maps to our traditional diskless compute nodes from the input side reasonably well. But as you're probably aware, it tends to create this burst problem that swamps the interconnect and often is delayed by the time it takes to access the disks. All right. One way that people have looked at resolving this kind of bursty output that we see is by using NVRAM servers that could be deployed as part of the parallel file system. But that choice really only alleviates the disk access time and continues to swamp the high performance interconnect and the storage area network. So something that's been commonly done, Cray has deployed data warp software in the past, is to deploy NVRAM servers as part of, that are directly attached to the high performance interconnect. This does a good job of alleviating the swamping of the storage area network, but it doesn't alleviate the problem of swamping the high performance interconnect. However, it does make it fairly simple to serve workload check output that are using this N-to-M or N-to-1 style. Nonetheless, it actually doesn't really address the problem. So when we look at what we did on a system like Sierra, we used on-node SSDs. And so if you're using the end-to-end model, it's pretty easy to use. You just write to that local storage, and then you can trickle that out subsequently to the parallel file system. So you really do a good job of addressing the problem of swamping the interconnect and moving that I/O traffic out of the main, causing interference with other jobs. Is also very useful for using for that swap or extended memory use case that I mentioned. However, it tends to be difficult to use for that shared file use case. And you can do it, and we do have a solution that works on Sierra and Lassen for that, but not as well as we would like. So another big issue is that if you allocate a job that's not making use of those on-node resources, then they just sit idle. All right. So if we think about how the rabbits work, this is really like building kind of little nests of PCI networks within the larger system. All right. And so then if only some of the compute nodes that are attached to that compute node are making use of it as local storage, you get good allocations. You can much more flexibly allocate the storage to different compute nodes. And in addition, we can actually use it as network attached storage, as I mentioned. So we can use it just as if it were those NVRAM servers directly attached to the interconnect. Again, that doesn't alleviate the problem of swamping the network. So one of the things that we're planning to do at Livermore is deploy something that we've been developing at Livermore called Unify FS onto the system and use the Rabbit processors to run that, but using the PCIe connections to access those disks, but with a file system that gives us shared file access. All right. Another key use case is actually one that I note here, which is that we can run analysis processes, either post facto or for in-transit data analysis in the containers running on the Rabbit processors. All right. So we plan to deploy one of these Rabbit modules for every compute chassis in El Capitan. We expect that using these Rabbit modules is going to significantly reduce system interference from I/O on the overall system. We're very likely to use it for caching OS files. We do this on Sierra. We find it significantly reduces boot times and basically makes the system much more efficient for the overall workload. When we were evaluating the responses we got to the Coral 2 RFP at Livermore, we found the Rabbit solution to be one of the key innovations that HPE was offering. And it was a significant factor in our choice of the Cray response for El Capitan. So in closing, I'll just say that El Capitan is going to continue the GPU accelerated era at Livermore, but it's also going to really move us to using a system level heterogeneity in our large scale production resources. And we've started doing that with the Cerebrus and Samba Nova systems that we've integrated into Lassen and Corona. And so with that, I will finish up just a little bit over what I was targeting. And we may just have to defer any questions to the panel that I'll be participating in later, but I'll leave that up to Kenta.